I'll just say, this is Andrew Gelman from Columbia is our second speaker. And he is not only in the stats department of Columbia, he's in the political science department. And he has a fascinating blog, or whatever it's called, that comments and has a lot of people who send comments to him about data issues in social science. Maybe say another word or two while you set up?
No, it's okay.
You're ready. Okay.
Is this on, or what's the deal with this? Oh, here. Is there a clicker for the slides by any chance? Sir, you have a clicker? Oh, thanks.
It only works if you're using PowerPoint.
Oh,
Or you have a PDF? Or
yeah.
If you're using Adobe Reader, it will work, but not Preview.
Well, here, let's try it and see, okay?
If you're using Adobe Reader, this one should work.
Let's try. Here, let's stick it in. So before beginning, I wanted to make a couple comments on the previous talk. Let's try to identify my keyboard. Do I need to do something to make this work? Oh, okay.
Let's just try to, maybe
Okay.
just try to close that. Off the screen.
Okay.
I think the first one. Screen layers.
No. How do you make it go forward?
Presentation.
You know, you guys are just too advanced here, I have to say. I'm used to, like at Columbia, we just use those acetate slides, and so it's really not such a big deal. We just, you erase them, and there you go. Okay, it works. Okay, how do you go?
This is
Okay. So I had a couple comments on the previous talk, which was fascinating, and one was that when you were saying that you were different types of people had different chance probabilities of being in your experiment, and so you did weighting in order to get it. You did weighting in order to. What's up with this? I guess I don't need the slides here. You did weighting in order to estimate an unbiased estimate of the treatment effect. And I think that's sort of okay, but once you have the treatment effect varying, I think you'd be better off modeling how it varies. So I think I'd recommend that you try multi-level regression and post-stratification and estimate how the treatment effect varies by the groups that determine the probability of response. And then if you do put it back together, you'll get something similar to the weighting, but you can expand it also. The other thing is, I have to say there's something that bothered me a little bit about this idea of playing a game with these participants. Like, so here we are, getting, let's say 5 or 6 figure salaries, and then you have these people like playing like to get like 15 cents. And like, so on one hand, I think, so there are certain things, okay, sure, like you're trying to get people to classify things correctly. So you want to set the incentives right. So if they're just answering at random and never getting it right, you want to boot them out, and you want them to know that they have that incentive. So you want like a game that's sort of open in that way. You say, look, we know that it's easy for you to just push and not look, but if you do that, you're not going to make money because we're going to boot you out. So you want people to know that. But at the same time, like I feel like the sort of social contract, like there's something where you say, we want you to do a certain level of effort and do your job well and we'll pay you, and that seems reasonable. But the idea that we're always trying to squeeze one extra bit of labor out of you because our profit margins aren't quite high enough here at Google or whatever, and we need a little more. I'm a little bothered by it because like it's partly, selfish, like poisoning the well thing, that like we will use such people to do answer surveys. And the usual social contract of these things is that you expect people are going to be sincere in their responses. Now, sincerity is a little different. I mean, you don't want people to put zero effort, but sincerity actually requires a little bit of effort, right? We all know that in real life, right? Insincerity just requires a few drinks, but sincerity, you have to actually sort of think about what does that mean. And if I'm doing a survey, not a classification task, I can't actually incentivize people to be honest. I mean, that's very difficult. So I'm sort of relying on the idea that they feel they're being paid fairly to do their job. And of course, I want the study to be interesting, so not boring, so they'll be motivated. Anyway, so if you're sort of out there like with an out and out like zero-sum attitude, like I'm just a little worried about that.
Can I just make one comment?
Yeah.
I think that's a really great point to make. And I think what you get probably is sometimes we should use non-monetary incentives. Because there's also other motivations to get people work, and that's totally interesting.
Yeah, it's complicated. I mean, because it depends on the task. I think if it really is like a classification task, then in some way it's very reasonable for people to be motivated to do it with least possible effort. On the other hand, if it's a survey response, you can't really play that game. It's just a different situation. So I want to tell you some stories, but this is basically how I've changed. So when I was a student way back when, I took probability, and I guess 35 years ago, I took a class in probability theory, and I took a class in stochastic processes. And then I took a statistics class, and they mentioned Bayesian inference somewhere, like this is, if you have prior information, this is what you can do. It seemed a little weird because the data are modeled so carefully and the prior information just get thrown in at the end. But then I was a graduate student here at Harvard, and my advisor was really into Bayesian methods. And by the time it was over, I felt pretty clear, like Bayesian statistics was not about prior information. It was really about structuring a problem. It was about, my co-author John Carlin called it the quantification of uncertainty. And when we wrote the first edition of our book, we were very careful. We had very little prior information in the usual sense of the word, like prior distributions. It was almost all, like everything, all the hyperparameters can be estimated from data. And then in our second book, it was the same thing, in our multi-level modeling book, how like multi-level modeling is just like a way you just estimate everything from data. That don't worry, it's not like really a prior at all. And it's really like downplaying that whole thing. But then I've sort of become changed, because then I started realizing I would come across problems where I realized that, I mean, there were different things. My estimates weren't as stable as I thought I thought they were. And I felt I needed a little bit of regularization. And this is something you find when you do something over and over again, you start to notice that. So if you look at statistics books and like statistics articles, things are typically framed as, here's a data set, here's our analysis, we do it once. And you tend to take your analysis too seriously. We all do this. So Bayesians will fixate on the posterior distribution, like that's the goal. But of course, it's not the goal, right? It's just a statement of uncertainty. Or the computer scientists will like worship cross-validation. But of course, the best cross-validation solution is itself just a random variable, right? It's just a function of data. It's a statistic. And I was in situations where I was working with some colleagues in political science who are fitting multi-level models as I asked them to do, and they'd fit them to data set after data set, different survey questions, data from different years, and you'd notice these hyperparameter estimates jumping around all over the place. And I started to realize that, I mean, it's no surprise, right? But there's a lot of uncertainty there, and we can regularize with just a little prior information. So I went around talking about weakly informative priors and how just a little bit of prior information can make a difference. And it's a little, those of a certain age will remember the Laffer curve from economics, but it's a little like that. Like, you want a little bit of prior information, like you want a little bit of taxes to help things run, but you don't want to tax people to death, and you don't want to put in so much prior information you can't learn from the data. I never wrote this paper on weakly informative priors that I wanted to write because I could never quite formalize this. The idea is that here's, like, I have, like, there's a true prior, a true distribution of parameters that might come in, and I have my belief, which is like my subjective prior, and that's not right. So the theory is that, because it's just my guess, so the model would be that I should use something a little wider than my subjective prior in order to capture that uncertainty, but not too wide. And in a lot of individual examples, we could get to work, but it was hard to understand in general. So I got a little stuck there, but I did feel that weakly informative priors were important. Then I started to think like actual prior information is important. So I've been moving towards really informative priors. And a lot of prior information is out there. I'd been using prior information informally. So I mean, this is not just about me. This is about you, right? So I'm trying to have you shortcut my decades of development and just get to where I am now. But it helps to see how I got here. So what we do is we have inferences and we say, hey, this doesn't make sense. I'll give you an example. I say, oh, this doesn't make sense. So what does that mean, it doesn't make sense? It means you have prior information, right? Because it looks wrong relative to something you already know. So we're always using our prior information, but maybe there's an advantage to putting it in more formally. And that's the topic of today's talk. Some of you have seen this example before. It was something somebody sent to me by email, influence of Valentine's Day and Halloween on birth timing. And I think people thought that I would make fun of it. They sent it to me, but I kind of liked it. This paper had a graph, had two graphs here. The number of babies born, they had data from 11 years of birth, just the number of babies born every day in the United States for 11 straight years. And the number, isn't that cute? You see, it's Halloween. And then the week before and the week after. And then they have, no, this is Valentine's Day. It's that, you know, isn't that cute? And look at Halloween with the witch. Isn't that adorable? So, and you see there's more people born on these special days or fewer on this day, and compared to the week before and the week after, and it's statistically significant. Now, I actually want to, this is not a bad analysis, but I just want to say something about statistically significant because this is a conference on big data, and yet there's this funny thing that, like, in the world of big data, all these things that shouldn't seem to matter with big data, like statistical significance and uncertainty, keep coming up. So we, in some sense, we never really have enough data. And a lot of big data analyses have a little data flavor. No, not always. There are really big data analyses where, like, you know, that computer program they wrote to play Pong. I saw that talk. That was really cool. It's just there's no p-values or uncertainties. They just wrote a computer program to play Pong, okay? That was very impressive statistics. But a lot of things we see that seem like big data, we end up at the end saying, well, is this really significant or not? How could that be like significance? How could that matter if you have a kilobyte, what am I saying? A terabyte of data or exabyte or whatever, running out of letters there, byte of data. Because you're comparing to variation, right? So I see some effect, but is it exist in other groups? Is it going to persist next year? There's variation at that level. So we always often have small n at the level of variation we care about. Anyway, they did this, and my question was, I'm a little worried because there's only 30 days here. I want to see all 366 days. So I asked someone made a graph. This is all the days of the year. You can ignore the smooth lines. Fewer people born on New Year's, July 4th, and Christmas. More people born between Christmas and New Year's because the baby has to come out sometime, right? And it's actually interesting. Here's February 29th. It's, what's interesting is that here is Valentine's and here's Halloween, and it looks like it's showing up, but it's hard to be sure because there's so much variation here anyway. So now this sort of puts us in a new level of uncertainty where we wonder whether we're just sort of grabbing patterns. There's a variation here. There are about 52 of these cycles in the year because this is not a 28-year cycle, so there's some confounding of day of week with day of year. And as I'm sure you know, fewer babies are born on the weekend. Let's see, go forward. This was a graph that someone sent me, which I kind of liked because it looks really pretty and I hate it. It's horrible graph. This graph tells us that, this graph tells us that more people are born in the summer, but it's hard to see how much, whereas here you can see it very clearly, numerically. And this graph also allows us to compare the 19th of every month, which is a useless thing. So remember that all graphs are comparisons. So like, you know, I used to say this, like, this is a message to you, by the way. You know how they say, don't put a sentence in the paper that you don't want somebody to read, right? Don't put numbers in your paper that you don't want people to actually read. So that table 3 of your paper, just get rid of it right now. But also with a graph, like, don't give people comparisons you don't want them to, you're not interested in seeing. Anyway, what we really need to do is decompose a bunch of things here. So we fit a decomposition model. So Aki Vetteri fit this model. It has it's an additive model with a slow trend, saying there were years where there are fewer births and then more births. There's a non-periodic component, which are these variations, which are just things happen, right? Like the economy is going well, maybe more people decide to have babies that month, you know, maybe some famous baby is kidnapped and people decide not to, you know, whatever it is, things happen. We have day of week effect, fewer babies on the weekend. We index this by year, and in the later years, the day of week effect is larger, which makes sense because from 1968 to 1988, there was an increase in the proportion of induced births. Seasonal effects, more babies born in the summer because more people are making babies around here. And finally, we have day of year effect, and we did not look for Halloween, we just put in 366 effects. Plus a few extra because there are some floating days, like Memorial Day, Labor Day, Thanksgiving, they float. So we added those effects. So we just put something in for every day, and there you see fewer on Christmas. Now Halloween is recovered and Valentine's Day is recovered. So this is a wonderful success story of statistical modeling that you can pull this out much nicer than those original graphs. But it's fine what they did because the people published their paper, which allowed us to move forward on that. I think the leap day is kind of funny because to me, like as a nerd, like I think it would be cool to be born on leap day. I have a friend who's 13. Like I just think it's hilarious. But I think most people are like, leap day, then you don't get a birthday. You know, that's no fun. So I don't know, people, what they're like. Anyway. We got more data. This is through 1988. Then the series stopped. But then there's another data set from 2000 to 2014, and we fit it. Now, this looks kind of similar, although I want to show you, look at the bottom graph. This goes, here's Christmas here. It's at 80. Now I'm going to show you the more recent one. Now Christmas is at 50. So actually, there's so many induced births now that Christmas, only half of people are born on Christmas, half the rate. The day of the week effects have become constant pretty much. Things haven't changed much since the year 2000. Here, the seasonal effect. We also discovered that there are now slightly fewer people born on September 11th. I'll blow up that last graph for you. And here's New Year's and Christmas. Somebody asked us about the 13th of the month, and you can see there it is. And you can even see Friday the 13th if you want to look for it. It's not in this particular model. I want to show you something that I don't like about the model, though. And look at this second. Well, there's different things you can see here. One is that the dips at Christmas and New Year are not fully accounted for by the rises in the days before and after. Another thing you can see is the second half of November not November, September, there's an excess of babies for 3 straight weeks. Now this violates the baby has to come out somewhere principle. And that principle's not in our model. Oh, here's another one around there. But that principle's not in our model anywhere, because if you go to our decomposition, we have these functions which are Gaussian processes, and then we have a bunch of delta functions. So what we should really have instead of a delta function for each day is a function, a kernel with 0 integral. So you should have a kernel that goes like down and then peaks up and down and up, right? Like this. Well, I don't have Blackboard, whatever. You get the idea. You should have a kernel that goes down and then goes up and then goes down and has an integral of 0. And if you do that, we haven't done that. That's more labor to relate to the previous talk. Nobody has incentivized us to do that. But there's something funny, because it will ripple back into other aspects of the model. Because what's going to happen if you make these ringing functions? So this rise here is going to go into here, right? Because it has to go into the seasonal effect. It has to go somewhere. So if you look at this, this is too smooth. And that's why there's too much. If you go to the previous graph, this is more bumpy, which is kind of right. It seems funny. Why is it bumpy? I don't know, but it is bumpy. So the hyperparameter of the Gaussian process got estimated well here, because we used an approximate algorithm where you get point estimates for the hyperparameters. We didn't do a full Bayes here for computational reasons. This one, the hyperparameter got estimated at the wrong value. Now I want to say this because we're just so used to estimating the hyperparameters, and I'm sure this conference there's going to be some talks about approximate computational algorithms, and you can use variational inference, and it's super fast. I have a paper where we use variational inference, it's super fast. But you got to remember, these things aren't perfect, because if you rely on a point estimate of a hyperparameter, this can happen to you. And we noticed it because of this, but in a sense, we're getting the wrong parameter there. And again, this is, like, for me, it's a kind of a big data problem. I mean, it's not big data for you, but for me, 20 years of birth data by day is a lot of numbers. It's such a big problem that we needed to use a different algorithm to fit. But yet, it's not really big enough to estimate this hyperparameter so well. And I should also point out all of the little features that go into the model, like letting various things vary over time. I think if you go back, how the day of the week effect varied by year, I think the day of year effect should vary by year too. We should probably have a multiplicative model in which the same factor that's blowing this up blows these up, so in later years these effects are larger. But lots and lots could be done. Which also suggests, thinking about statistics and computer science, that what we need is not just a method to fit models, but we need a workflow. We need a way of fitting models and checking them and going beyond that. How much time do I have?
Quite a bit of time left.
Oh, 29 minutes. OK, good. OK, so there is a saying that we have in statistics, the blessing of dimensionality. I'm sure you've heard that. And this is related to that there's a mathematical saying that it's a true mathematical saying that if you have a hard problem in mathematics, often the way to solve it is to embed it in a larger problem. You've heard this, right? Like if you want to sum an infinite series, make a generating function. Figure out the generating function, then plug x equals 1, and then you have the sum of the series. It sounds hard to believe, but it's kind of true. If you want to prove some obscure or not so obscure theorem, try proving a generalization. Don't prove it on prime numbers, prove it on ideals, whatever it is. This is something we learn a lot about in math, even algebra in a sense. A lot of things, arithmetic theorems can be proved more easily in algebra. So it's true in statistics also. was not only that we learned more by looking at all 366 days than just looking at Halloween and Valentine's Day, but we actually learned more about Halloween and Valentine's Day by looking at all 366 days, because there's nothing so special about those days. And so I want to briefly talk about what happens if you don't do that. This is a paper that came out a few years ago in the leading journal of psychology. The fluctuating female vote. It claimed that they did a survey and they found that women at a certain time of the month were about 20 percentage points more likely to vote for Barack Obama for president. And the theory was basic evolutionary psychology, which is that Obama is like the girly candidate and women are more girly at that time of the month. And no, it was actually more, not quite that. They found an interaction with marital status, so the single women were more likely to support Obama, and the married women at that time of the month are more likely to support Romney. Was an interaction. But that kind of makes sense because Romney is like a married woman's kind of guy. He's like a beefy guy with 6 kids, brings home the bacon. Obama's like young, dangerous, he's a foreigner, and I'm always worried that people aren't going to laugh at that one, it's always, and so, there's sort of a story behind it, and so they published it in the top journal of psychology, and okay, so there were some issues. What they found was statistically significant and a large effect. Now, there are a bunch of choices in the data analysis. These are not actually choices in the statistical model. These are just choices in how to code the data. There's a lot of options in how you code the data. We went through other papers by the same authors to see how they coded their data in other problems. And there are many options. 168 degrees of freedom here. And we decided to do what we call a multiverse analysis, which is we got their data and then we replicated their analysis on using every one of these choices. And these are all the different confidence intervals for the effect. And this is the one that they reported. This indicates this is a kind of problem where there's an incentive for the researchers to put in more effort. So I think we didn't need to do any manipulations, and I'm so glad about that previous talk. It was just perfect. Now, actually, I should say that when you do this, you don't always get something so, null looking as this. If you actually want, just as an aside, this is the confidence intervals. You can also show, I also have a histogram of the p-values. If you ever want to do this yourself, we have a paper on it. I think what you should do is do all the analyses, and if you want a p-value, take the mean of all the p-values. Not the mean of the logs of the p-values or anything cute like that. Just the actual mean of the p-values is going to sort of give you the right answer if you think it through. The funny thing about the mean of the p-values is you only need a few that are like high in order to destroy that mean. So this is sort of what would have happened had they did things right, although then they wouldn't have published their paper, of course. But it's more than that. It's not just that, okay, look, if they'd analyzed their data correctly, they wouldn't have seen anything. Their study never had a chance to. We're going to get back to the base stuff, by the way. So, as I said, they found an effect size of about close to 20 percentage points, how much different you voted based on what time of the month it was for you. I know, because I've done survey research, that during the period of their study, almost nobody was changing their vote preference. So I'm going to say that any effect, any difference between vote proportions under different times of the month has got to be less than 2 percentage points. It's got to be less than 2% of the women who are actually changing their view based on that. Suppose the effect size is really 2 percentage points. It turns out that the standard error of this study was like 8 percentage points. So these, maybe I think it was, yeah. these red bars are plus or minus 2 standard errors from 0. So let me start here. If you do this study, if they had done this study and their estimated effect size had been anything less than 16 in absolute value, it wouldn't have been reported. Because you're only allowed to report statistically significant things. Because you don't want to go around reporting noise, right? Polluting the literature. So the only thing that could be reported would be these things in the red zone. Now, if the true effect size were 2 percentage points, this is the probability that you would actually see something this high, and this is the probability you'd see something this high in the other direction. So the point of this picture is that anything that's reported has to be at least 9 times the true effect size, no matter what. I mean, that's what I call a bias. A factor of 9, like not just an expected factor of 9, but like a hard bound of 9. It has to be 9 times bigger than the true. That's why I said the study is dead on arrival, because they didn't have a chance of finding anything useful. Now, of course, I'm using prior information there, because I want to, learn about the world and not do stupid things. Right. It's a lot of confusion about this in different literatures. This is from a criminology paper that somebody sent me. It's a well-known paper in the field of criminology. And it goes like, they talk about this. They say, first, it's commonly assumed that increasing the size of a sample provides the most straightforward method of increasing the statistical power. So the first paragraph says that everybody knows if you have a bigger sample, you get more power, so you should do bigger sample size experiments. But there's something else. These criminologists are not so stupid, that when they do large sample size studies, they're not routinely finding statistical significance. In fact, they find statistical significance just as often in small studies as in large studies. This doesn't seem right. Large studies should have higher power, but yet they do. So why is it? This is a puzzle. It's called Weisberg's paradox. And their response, which I disagree with, but what they wrote is that difficulty in maintaining the integrity of treatments and the homogeneity of samples offsets the design advantages of larger investigations. So what they wrote was the trouble with large studies, they should have higher power, but when you do a larger study, you sort of run out of energy, you sort of lose interest, it's hard to keep quality control, you let just anybody into your study, and as a result, things get much more noisy and you lose that power advantage. And that sounds very plausible. I don't see any evidence for it, though, or not much evidence for it. So I think the problem is not that the large studies are crappy. It's that the small studies, the question is, how come these small studies are so successful? And the answer is that people have a goal, which is to get statistical significance, and they'll get it one way or the other. So people have close to 100% power. Whenever you do your study, you get a result, and you find something significant. The small studies have that too. So that was my argument. But the point is that people are thinking about these issues. They're aware that there are these issues, even if they're thinking about the wrong way. This is somewhat analogous to trying to come up with a mechanistic explanation for regression to the mean. I mean, there's sort of a systemic problem that people are trying to understand in the wrong way. This comes up in my own research. I'm not going to go into the details, but we did a study in which the culmination were these estimates of causal effects. They're somewhat identified. I won't get into the details. There are, I think, 14 of these. 4 of them are statistically significant. If you look at it carefully, I'll tell you that the average seems to be positive. There's more positive things going on than negative things. We did some placebo control type things. I actually think there's something going on here. And I think in the old days, I might have picked these 4 things and told stories about them. When we change our analysis in different sort of non-trivial ways, sometimes things move around and different things become positive or negative. There's just not enough signal here to learn too much from this. And I think the problem here is that I don't have really enough. These are very small effects, and I don't really have enough data or good enough measurements to understand them that well. So I have to recognize that. So it does come up in my own work. I have another example which I'll skip. It's just another example illustrating how these problems occur. Now I want to move a little towards statistics, towards Bayesian statistics, and I will give you my favorite example. It's this model. Have you seen this before? It's just actually, I give this one data point which kind of upsets people. So imagine you have a lot of data points, and this is y is the mean of the data, and 1 just happens to be the standard error of the mean. Or it's a regression coefficient. Y is a regression coefficient, whatever. Okay, this is my evidence. And I have a flat prior. This is what it usually do, right? You just take your data and do that. Do this all the time. Now I have data. My measurement is y equals 1. So my estimate is 1. Oh, by the way, this is where you're supposed to really focus here. So you back there, yeah, this is your chance. Don't, yeah, thanks. Okay, because this, you can follow this. It's just one slide here. Okay, so you observe y equals 1. It's not statistically significant. I mean, not statistical significant. It's noise. It's noise. The definition of noise. It's one standard error away from 0. Okay, nothing going on. Now I'm going to do some Bayesian inference. Well, here's my posterior distribution centered at the estimate of the standard deviation of 1. And the posterior probability that theta is greater than 0 is 0.84. Now, you know, we're so used to seeing this all the time, but as I like to say, that one of the qualities of a good researcher is the ability to be upset about things. And we should be upset about this because this is ludicrous that you would bet 5-to-1 odds based on complete noise. I mean, would you? I would not. I would not. Like, someone does some study, and this is the result they get, and then they want to bet, what's the true effect? Like, we could do a huge replication, whatever. Do I bet? Do I think there's 5-to-1 odds that this is going to replicate in the correct direction? Of course not. Of course. I mean, there are a couple people at Harvard who are on the record as saying they believe this. There's a psychology professor here who said that the replication rate in psychology is statistically indistinguishable from 100%. But that's just stupid. This is not right. And the thing is that we don't usually deal with this because as Bayesians, we don't make this bet, right? So there's a principle that statistical methods are not as bad as they statistical methods tend to be better in practice than in theory. Because the worst things that you could do, you don't do because they're such a bad idea. Okay? And so we would never make this bet because we know that it just looks consistent with noise. But the issue is there's a saying, a Bayesian saying, which is that with great power comes great responsibility, right? And I bet you wondered what this guy was doing there. And so this is bothersome that our Bayesian inference comes up with this horrible, our default Bayesian analysis comes up with this horrible answer. And our only solution is we know not to look at it. Like, we just sort of look away from that because it's so uncomfortable. Now, the right answer, of course, is that we have prior information that most effects are the effects tend to be closer to 0 and not so likely to be larger. If we were to reframe this problem, 0 is special here. So the statement, this is only one standard error away from 0, is already giving you prior information because why were you using 0 as a baseline? The point is that we can formalize this. Now, interestingly, I think that all problems of multiple comparisons can be entirely resolved by using informative priors. Well, if you use the correct prior, okay. Obviously, nothing is going to be correct, so we have to worry about that. But if you're in a situation where you're worried about multiple comparisons, if you partially pool things towards 0, that will actually completely eliminate the problem. You'll only get the appropriate number of comparisons that you want. The other thing about this is I think you look at this and you say, well, this is fine, but this would never happen to me. So I want you to replace this 1 by a 2. And if you replace the 1 by a 2, the 0.84 gets replaced by a 0.975. And the funny thing is that lots of people who would never dream of taking seriously something that's 1 standard error away from 0 will act as if something that's 2 standard errors away from 0 gives them that 40 to 1 odds that they want. But it's the same problem. It's even worse. When y equals 2, the prior will have even more of an effect, and you'll need to do even more partial pooling. This is my concluding slide, what we should do. So I have some solutions for you. Do I have another minute? Okay. So I have a couple solutions. So some of these are kind of new. Scale-free modeling, this is not a new idea, but it's new to me. I want all my parameters to be scale-free. That is, when I put priors on things, I don't want to have a parameter that the units are kilograms, or minutes, or hours, or test scores. Everything should be scale-free. So for example, that problem where you get someone on a scale and then they get off the scale and you weigh them and what's the prior for their weight, I don't want to say my prior is somewhere around 150 pounds. I want it to be, let's say, relative to the mean and standard deviation of people, or men, or American men, or middle-aged American men, or something like that. Well, this also indicates there's more than one way to be scale-free, but any of these solutions are going to be reasonable. Where did I learn about this? In 2 ways. One is we're doing a lot of work in pharmacology. And in pharmacology, you have these parameters, like someone has a prior, and it's like 0.00, I think it's between 0.004 and 0.006. Like that's their prior, so don't use a uniform prior, use like a log normal, so we're doing that. And then, like, where did this come from? And they say, oh, well, that's because 0.005 is a standard value for blah, 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 and then we're not quite sure, we want to be off by plus or minus 20%. So then what you have to do in your model is put that 0.005 into the model as a number. Say, there's some value, and then say, I think I'm uncertain in this range. And then you might even be uncertain about that 0.005 also. But a lot of parameters are like that. So you want it's like people are trying to do a shortcut. They're saying, oh, what's my prior in this parameter? Often my information is coming in pieces. Put the pieces in separately. It's also for computational reasons that if your parameters are on unit scale, then a lot of computational algorithms like HMC or variational inference are much more stable when all the parameters are on unit scale. If you have parameters like I ran a regression and I was predicting something as a function of population of countries, so the numbers are in the millions, so the coefficients are like 0.00003, then you get really bad geometry in your inferences. Now, the funny thing is that when I learned statistics, they didn't tell me about that. Because if you learn in classical statistics, linear transformations don't matter. And in fact, it's often a point of pride of researchers to not touch their data. They're worried about those degrees of freedom. So they don't want to touch their data, so they put their data in exactly as coded in the data file into their model, and then you get these really weird coefficients, but it doesn't matter what's a linear transformation, it propagates through. Once you have prior information, all of a sudden it does make a difference. So I think that scale-free modeling is what we should be doing. It's just, I love it. It's a great conceptual idea. It's so easy to think about, and you can immediately apply it in all your problems. Weakly informative priors, I have given entire talks on that with lots of examples where a little prior information gives you a lot of regularization. My new thing, like in Stan, if I'm fitting a model, is to put normal 0, 1 priors on all the parameters. Except the positive ones, like the standard deviation parameters, I put normal 0, 1 priors on them constrained to be positive. Now, that just seems so weird at first. Like, you think about that, and it's so goofy, but to just give an Olympic-themed story. Remember when they first did the high jumps and they started jumping backwards? Well, that seemed weird too, and now that's what they do, right? So it sounds so weird, like normal 0, 1 priors on everything, but it really helps with a lot of problems. Of course, there are problems which it's a bad prior. Well, this is a default model. Defaults don't always work, so if you have information beyond that, but I think we should be scaling things so that that works. I mentioned the multiple comparisons problem. Again, I could give a whole talk on that. It's really fascinating, but you really, honestly, really don't need to do these things like corrections for multiple comparisons if you fit all the model, if you do all the comparisons and you use the appropriate priors. There's a connection between computational and inferential stability. So you know about the Folk theorem of statistical computing? Do people know about this? That when you have a problem with your computing, it often is a problem with your model. Not always, but often, right? So that's like, the Folk theorem helped us think about things like the normal 0-1 priors and the scale-free modeling, that sometimes you have problems getting variational inference to converge when you have parameters that are on much different scales. But why do we have parameters on much different scales? Really, I've almost never seen a problem where that would make sense. When they're on much different scales, you sort of know it ahead of time. You can put them on the scale together. Now, it's also, you know about this, you all computer scientists, that like all algorithms are iterative. We used to think that like if an algorithm needed a little bit of hand-holding, if you need to give starting values, that was somehow cheating. But now we realize that in general that's necessary because, you know, the world's a big place, right? You know, in 50 dimensions, nobody can hear you scream, right? So of course you have to know where to look. The fact that there are certain algorithms that converge, you know, linearly, quadratically, whatever, can't mean that in general. Finally, the implications for big data, since this is a big data conference, that when you have big data, it often seems to come down to those little data questions at the end. You do the big A/B test, the big this, the big that, and at the end, you're trying to decide some question like, you know, do the Iraqis have weapons of mass destruction? And all the remote sensing in the world is still saying, well, I'm not quite sure, you know, what do you do? Or all these people do the A/B test and then they say, well, we're going to just only make the decision if it reached the 80% threshold or the 90% threshold, and whatever it is. All the data in the world come down to dealing with uncertainty. And I think prior information can really help, both computationally and in a real sense in avoiding us doing stupid things.
For the talk, but it was a marvelous talk and comments and questions. We have a few minutes. Yes.
Yeah, so I thought that was really awesome. I guess I have a very practical question for you, which is, I'm at Facebook. I'm really interested in getting better than just point estimates of a lot of things that we care about. But often we're doing things like trees or like, you know, like not these kinds of like linear models. And often it's really hard, you know, one thing we could do is like try to do like a bootstrap, but then you have to fit a lot of them and it's really hard. And so, you know, how should we think about getting uncertainty estimates from complicated models?
This comes up a lot in my applied work, that I'm working with people and they did the tree or whatever, a complicated model, and we're using it as input. And sometimes what we can do is, I think this is sort of a great area of research is to how to interface these things. But what we've done so far is that we take the output from the machine learning method and then feed it into a hierarchical linear or generalized linear model. So like we had something where I can't tell you the details, but it was a certain example where they were measuring some success. And they fit a complicated machine learning model. Then we took it and we put it into a logistic regression. We used, as the predictor in the logistic regression, the logit estimated probability of success from their machine learning model. And if everything is super clean, it would just have a coefficient of 1. But once you throw in other factors, then the coefficient tends to become a little bit less than 1 and so forth. So that's what I've been doing.
More question?
Okay.